Section 10.6, we're looking at the relationships and how to find measurements of line segments in relationship to circles. So specifically chords and secants. So our first or our essential question is, what relationship exists among intersecting chords and secants? Our first theorem, segments of chords theorem, which says if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So we're looking at the picture here. We have A, B, and C, D that are chords. The product, multiplication of the lengths of the segments of one chord. So if we do AE times EB, that's equal to the product of the lengths of the segments of the other chord. So CE times ED. Right, so we multiply these two numbers, it'll be equal to when we multiply those two numbers. So example 1, we have the picture here with the two chords. 6 times x is equal to 5 times 12. So 6x equals 60, and x is 10. Example 2, they make a little bit more complicated for us. 1, they're asking for us to find ML and JK, but also they give us x's everywhere, right? Which makes our setup a little bit harder. Helps if you can see the problem. Right? But we start off the same way. I have JK as one side, so that's x plus 5 times x, and then x plus 3 times x plus 1. Okay? As we do the other one, as we do LM, so x squared plus 5x when I distribute in that x, and I'm basically distributing x plus 3. You may also think of it as FOIL. All right, x squared plus 3x plus 1x plus 3. I do x times x, 3 times x, x times 1, and 3 times 1. Okay. So nice thing here, x squared will cancel. Right? So I have 5x. Combined here, I have 4x plus 3. Subtract the 4x, and I have x equals 3. Okay. Now they asked me for ML and JK, which is the full lengths of the lines. So if I plug in my 3 here, I have 3 plus 3, which is 6. 3 plus 1, which is 4. So ML is going to be 10. And here, 3 plus 5 is 8, plus 3. Then JK is 11. Right, now the segments of secants theorem. Okay, now we're looking at lines that go outside of our circle. It says if two secant segments share this same endpoint, all right, outside of a circle, then the product of the lengths of the one secant segment and its external segment equals the product of the lengths of the other secant segment and its external secant segment. How I like to say this is that I'm doing the whole times the outside part. All right. So when we're looking here, we have EB as the whole top line times EA, which is the outside part. That is going to be equal to ED, the whole line, times EC, the outside part. Okay. Sometimes we'll need to look at things, we'll have problems where I have X in a weird spot that causes some problems, or I have to add things up or subtract things to get what I want. So when we're looking at example 2, right, when I'm looking at PR, the whole is 10, 4 plus 6. Okay, so So that's 4 plus 6 gets me that 10. The outside part is 6. When I'm looking at RT, the whole is 5 plus X. The outside part is 5. So here I have 60. Here I distribute. I have 25 plus 5X. Subtract the 25. I have 35 equals 5X. And X then is 7. Okay. On this problem, if the X is on the outside here and the number inside, that gets a bit more complicated. You then have the X squareds, right? But with the X inside, it is not that bad. Okay. Example 4 is much more complicated. I think I'll come back to example 4 at the very end. All right, that is one of the harder problems and deals with factoring and stuff like that. So we'll come back to that concept at the end. We'll hit on segments of secants and tangents theorem first. All right, and look at our different relationships here. So I'll read through this in a second. I still think of this as whole times outside part. The difference is with your tangent line, the whole and the outside part is the same thing. Okay, so they read it as a different theorem. It says if a secant segment and a tangent segment share an endpoint outside a circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So the square of the length of the tangent segment is because the whole and the outside part is the same. So we look at example A, right? On the line in the bottom here, I have the whole, which is 5 plus X, and the outside part, which is 5. And then the tangent, the whole and the outside part is the same, which is I can look at as squaring it. Right? So I have 25 plus 5X equals 100. So 5X equals 75 when I subtract the 25, and X is 15. B, whole is 4, and the outside part is 1. Other is X squared. So this one's nice and easy. We have 4 equals X squared. So X, take the square root, I get X is 2. All right. C is the one I mentioned before where we have the X on the outside. So the one side is nice. I have 4 squared for that bottom part. The whole times the outside part, I have 6 plus, or the whole, I have 6 plus X. But the outside part here is X. All right, so actually we have to FOIL this one too, which is similar to the one I mentioned above. We have 16 equals 6X plus X squared. So here I don't have anything that foils or that cancels. So I have to move everything to the same side. I have X squared plus 6X minus 16. All right, so this is the same thing we'll look at above here. We're going to have to multiply two things. So I'm looking for I have X and X. I'm looking for something that multiplies to 16 or negative 16 and adds to 6. All right, so when I'm looking at the factors of 16, that's going to be plus 8 and minus 2. All right, so I'm looking at like 1 16 times 16, 4 times 4, 8 times 2 is 16. Those two will add up to 6. And then either thing will be right here. However, this is geometry. In algebra, my answers would be X equals negative 8 and positive 2. Geometry, that can't work. This can't be a negative 8. So my answer is just X equals 2. And then D, 15 squared, whole times the outside part, equals 9 plus 4X as my whole, times 9. So I have 225 equals 81 plus 36X. 36X equals 144. And X equals 4. And I'm going to go up to this last one. We'll look at the factoring a little bit longer on this one. So this one's nice and messy when we look at it. Now we're back to our 2 secants. So we have whole times outside part. So I have 3 plus x plus 2 as my whole times 3 as my outside part equals x plus 1 plus x minus 1 as my whole times x plus 1 as my outside part. Okay, so that's very messy looking. As we simplify it, it's not super bad. We have x plus 5 times 3 on one side. 1 and negative 1 cancel, so I have 2x times x plus 1 on the other side. So I just distribute, so that doesn't seem that bad right there. I just distribute. The problem is when I distribute, we get 3x plus 15, we get 2x squared plus 2x. Okay. So nothing's going to cancel nicely there. We move everything to the same side. All right, so I have 2x squared minus x, because I subtract the 3x, and minus 15. Okay. So again, now here I'm going to have to factor this out, right? Because I'll go through it a little bit more in depth on this one. Because this is negative, I know when I'm multiplying, I'm going to have a positive and a negative here. Right? I also know I'm going to have 2 x's in the front because of the x squared. And I want something that multiplies to negative 15 and adds to negative 1. Right? So normally, if this 2 here makes things a little bit ickier too, which we'll get to in a second. If I'm dealing with just the 15, I'd be looking at 15 and 1 and 5 and 3. Because those are the only multiples that get me to 15. That's still what I'm looking for to plug in here. The difference is I have the 2. Right? So now I need to consider the 2. Well, if I look at 15 and 1, there's no way I'm getting them within 1 of each other, even with multiplying by 2. But with 5 and 3, if I do 10 and 3, it's not 1 away. But if I do 6 and 5, they're 1 away. So I'm going to have the 2 times the 3. Since this is negative and 2 times 3 is the bigger part, I want the 3 here and the 2 here. Also, I put the positive and negative. That's just random. You could switch those. All right, I did it this way. So then the 5 goes here. So when I distribute now, I get 2x squared, 5x, and negative 6x, which gives me negative x, and 5 times negative 3, which gives me negative 15. Okay. So again, as I mentioned before, when I'm looking at this, I need these to be positive because they're actual line lengths. So normally for this problem, negative 5 halves would be an answer. That does not work for geometry. So for geometry, the only answer is x equals 3. And we went a little bit off the paper there. Or off the screen.